All right, so we're going to do the same thing. We're going to do inference and confidence intervals over comparing two proportions. Okay? So really same procedures. We add some different formulas. Good news is these formulas are on your formula sheet. This is what we're going to do today. We're going to look at the sampling distribution of sample proportions. And then check what conditions need to be met. We'll construct a confidence interval, and we'll look at how to do a hypothesis test, or do inference, or a significance test, whatever you would like to call it. So if we had two populations, population 1, population 2, and there's some character of interest, right? In this case, it's going to be a proportion. I think that what we wind up looking at is the proportion of students that do their homework throughout this. So we're going to compare them. If we're actually looking at an experiment, we'll actually consider our parameters P1 and P2, these proportions, to actually be, well, it's considered to be a parameter. It will consider that it's the entire population, right? So we're actually comparing the entire population of a control or an experiment group. And we'll actually, there's some ramifications for that later on in the lesson. Anyhow, moving on. So, like I promised, we're talking about schools. The difference between these two proportions. So, school 1 has 70% of students do their homework last night. At school 2, 50% did their homework last night. 20% of those just copied it. Just kidding. So, a counselor at school 1 takes a random sample of 100 students, gets a proportion for the amount that did the homework, and then we've got a counselor that takes 200 students. It's okay that those sample sizes are not the same. It is okay. It's all right. So if we were to found that proportion, what would we think would be true about the difference P1 minus P2? If P1 is the school with 70% and P2 is the school with 50%, we would imagine that P1 minus P2, or P hats of 1 minus P hats of 2 should be positive, right? It should be. If it's true that 70% of the students do their homework at school 1, which is the proportion P hats of 1, where they got that from, the population that they got that from. And it's true that at school 2, 50% of the students do their homework, which is where they got the proportion P hats of 2. If that's true, then it should be the case that P hats of 1 minus P hats of 2. It should be greater than 0. They took some Phantom software and generated a simple random sample of 100 students from school 1, 200 students from school 2, looked at the difference in sample proportions, and repeated the process 1,000 times. That is a lot of samples. The idea is what do you notice about the shape, center, and spread of the sampling distribution of P hats of 1 minus P hats of 2? And what do? If we're asked a question like that, what do we notice? You got to talk about it, right? So the shape looks approximately normal. The center is 0.2. So what do we notice about that? It appears that that center is actually mu sub P hat, right? Yeah, mu sub P hat 1, right? Minus mu sub P hat 2, right? We got 0.7 minus 0.5, 0.2. what do we notice about the standard deviation or spread of the two? It is not that, right? There's not actually a clear, I can't see that that it's one minus, it's the one minus the other, and it's going to be true that it's not. We're going to have a set formula for that. All right. And I believe we're going to introduce that right now. So we got some random variables. P hats of 1, P hats of 2. P hats of 1 minus P hats of 2 is the difference between the two random variables. We have learned that the mean is going to be just the mean of one random variable minus the mean of the other random variable. And our standard deviation, we're actually going to take the variance of the one plus the variance of the other, and that is going to be the standard deviation of our combination of these two random variables. So we're down to the nitty-gritty of this thing, right? So if we're comparing the difference in two proportions, conditions that we got to check, right? It's always got to come, each one of these two proportions must come from a simple random sample. We also are going to need to check for normality. So in order to look at, in order to say that the shape is approximately normal, we're going to have to actually do that n times p greater than or equal to 10 for both proportions. So you'll actually wind up doing it twice, just to check that both proportions, that the sampling distribution of both proportions is normal. And if that's the case, then the sampling proportion, the sampling distribution of the difference of the two proportions is also normal. All right. Like we said, the mean of that sampling distribution is going to be the one proportion minus the other proportion, as we looked at when we looked at the fathom stuff. And then here you go. Standard deviation is this groovy little formula. And I'll show you exactly where to find that on your handy dandy formula sheet. So if you look at your formula sheet, scrolling on down, kind of in this inference side here. So with our two sample, right? So counts. We'll have two samples. We'll have two proportions. So difference of sample proportions. We'll be looking at that top one under difference of sample proportions. So that's where you'll find it. Good thing you don't have to remember. You don't have to memorize it. You are gonna. The only thing you're gonna have to really memorize for this is what to do with a fooled proportion. We'll get to that here in just one second. So this is what the sampling distribution of p hats of 1 minus p hats of 2 looks like. Nothing big there, just looking at it. All right, so back to our schools. So we're going to describe the shape, center, and spread of this situation. We have some parameter p that we're using, and that we'll call that piece of 1 is 0.7. And then we have a parameter piece of 2, which is the 0.5, representing the 50% of the students at school 2 that did their homework. And we'll check that against our n sub 1, our sample size from school 1, and n sub 2, our sample size from school 2, to make sure that the distribution is approximately normal. And you can see there that it is. The mean is easy to calculate. And then for our standard deviation, we're going to plug that into the formula. No big deal. So if we're going to construct the confidence interval for p sub 1 minus p sub 2, we're going to follow this same pattern, right? Our statistic plus or minus our critical value times the standard deviation of our statistic. Pretty straightforward. It's going to be easy to construct. Conditions that we need to check are going to be the same. And here we go. Same conditions, right? And it's just that you have to check both proportions, right? So your 10%, you have to actually check against the sample size from your that you got your one proportion from, and then you're also going to have to check it against the sample size that you got your other proportion from, as well as checking for normality or your large counts. So if you don't know your parameters, p sub 1 and p sub 2, you may use a statistic, right? In this case, a sample proportion. So you would use p hat sub 1 minus p hat sub 2 as your mean, or your standard error method. You can use that as your point estimate as well. And then you would use that p hat sub 1 and p hat sub 2 in order to calculate your standard deviation. Yes? So you'll be given a proportion, either the population proportion or sample proportion, and then you will have to plug that. If you're actually given like a list of values and need a standard deviation, your calculator will do that, but it's not going to be using this formula because we're going to be looking at difference of sample means. So yeah, you're going to be plugging stuff into this formula quite a bit. So this is the exact formula that you'll use to calculate a confidence interval. And remember, right? When we did confidence intervals for proportions back in chapter 8, our critical value that we used was always Z star. So you got to think to yourself: proportion, confidence interval. Your critical value will always be Z star. If you are doing a confidence interval for a mean, whether it's difference of means or one mean, your critical value is going to be a T star critical value. Okay? So the same thing is true. Always, for proportion, your critical value is going to be a Z star critical value. All right, so we're going to do inference. I guess the book calls it significance test. Or a hypothesis test, if you like. I want to stress that, right, we're looking at the difference between the two. I want to stress that you use this one. If you stay consistent, you won't get yourself confused. So you can use the null hypothesis that they're the same, right? But if they are the same, then their difference must be 0, right? And I think it just works so much better once you plug it in to a formula to get a test statistic, because at that point, so when you're plugging in, I'm going to just move ahead and then come back. If you use that, then this is always 0. And it's just, you don't ever have to think. You just say, okay, cool. If I have two proportions, my parameter value is always 0 in that one, right? Because you have your statistic minus parameter is 0. So if you just stick with that and stay consistent, you won't make it. You'll be less likely to make a mistake. I think it's a better way to go. So that's why I like to stick with that one. And then your alternative hypothesis is going to be either of these things relating to, is that the difference of the two proportions greater than 0? Is the difference of the two proportions less than 0? Or is it just not 0, right? In one case, we have your left-tailed, right-tailed, and two-tailed test. Any conditions are the same. Exact same conditions as you would use for a confidence interval, which is true, right? It's always been true as we've been moving through this material. So your test statistic, always statistic minus parameter, divided by the standard deviation of your test statistic. In this case, like I said, keep your parameter 0. Your null hypothesis is always going to be there is no difference, right? And if you just keep it like that, life is much more simple. The most important thing that's on this page right here is this idea of this p hat sub c. So this is your pooled sample proportion. You have two parameters. They're not the same. But you're going to need a statistic to use in order to calculate your standard deviation of your statistic. That statistic that you're going to use is the p hat sub c. So you're going to put your count of successes, right, over your sample sizes combined, right? So in the case of, we don't have that. I have an example for the school one, and I don't. So, you know, if you had 2 out of 10 people made choice A and 3 out of 12 people made choice B, then you would have 5 out of 22 would be your pooled proportion, your pooled sample. So you'll just add successes over your sample size. So this pool value is very important because you're going to use it, like I said, in order to calculate your standard deviation. You will have to use a pooled value. And I think that's where people kind of slip up or get confused the most when they're doing these types of problems, is they won't use that pooled value. They'll get actually confused about what to use and wind up using something weird. Happens a lot. So be careful with that. Make sure to use the pooled value. And I would even add, you know, to this, I feel like it's appropriate to put it here, that p hat sub c is equal to x1 plus x2 over n plus x3. I think it's a good spot. And so if you're going to do inference for an experiment, and that's what I was talking about earlier, if your experimental units down at the bottom are not randomly selected, then you don't need to check the 10% condition, because it's assumed that they're the entire condition. Really weird. Anyhow, this slide, when I was looking at it, I was like, why is this slide here? It's, you know, it's all stuff that we kind of get. It's all from our experimental design unit, except for the last bullet, which is also kind of weird. Anyhow. There it is. So that is looking at difference of proportions and sampling distribution, how to do inference, confidence intervals, all in a nutshell, and we'll work some problems next class. And then I'll be able to give you guys some stuff. I don't know. So, this is what we did. I just said that. And next problem next class.